When you look out at the vastness of the universe, at the planets, stars, galaxies, and all there is out there, one fundamental question screams and begs for an explanation. Why is there something rather than nothing? The problem gets even worse when you consider the laws of physics governing our universe, which appear to be completely symmetric between matter and antimatter. Yet, as we look at what's out there, we find that all the stars and galaxies we see are made mostly of matter, with scarcely any antimatter at all. Clearly, we exist, as do the stars and galaxies we see. So, what intricate forces led to the asymmetry that birthed the world as we perceive it? What profound mechanisms unfolded to tip the balance and grant us this universe teeming with galaxies, stars, and the enigma of our own existence? And how did it happen? So, how was this unimaginably giant universe created? For centuries, scientists thought the universe always existed in an essentially unchanged form, running like clockwork thanks to the laws of physics. But a Belgian priest and scientist called George Joseph put forward another idea. In 1927, he proposed that the universe began as a large, pregnant, and primeval atom, exploding and sending out the smaller atoms we see today. His idea went largely unnoticed. But in 1929, astronomer Edwin Hubble discovered that the universe isn't static but is, in fact, expanding. If so, some scientists reasoned that if you rewound the universe's life, it should have existed as a tiny, dense point at some point. The celebrated astronomer Fred Hoyle sarcastically called this concept the Big Bang Theory, a phrase its proponents would later adopt. Undeterred by skeptics, scientists Ralph Alpher, George Gamow, and Robert Herman predicted that if there had been a Big Bang, then a faint afterglow should linger somewhere in the universe, and we should, in theory, be able to detect it. To do so would require one of science's greatest pieces of fortune. In the mid-1960s, astronomers Arno Penzias and Robert Wilson needed help tuning into the microwave signals transmitted from the Milky Way. Their radio antenna kept picking up a persistent, weak hiss of radio noise. Rebuilding the antenna couldn't get rid of the noise. That's because the hiss they tried so hard to remove was the echo of the Big Bang, or the cosmic microwave background radiation as it is known. If the Big Bang Theory is true, how did it lead to all the planets, stars, and galaxies we can see today? Thanks to a series of calculations, observations from telescopes on Earth and probes in space, our best explanation is this. Around 13.8 billion years ago, all the matter in the universe emerged from a single minute point, or singularity, in a violent burst. This expanded at an astonishingly high rate and temperature, doubling in size every 10 to minus 34 seconds, creating space as it rapidly inflated. Gravity and all the other forces were formed within a tiny fraction of a second. The energy changed into particles of matter and antimatter, which largely destroyed each other. But luckily for us, some matter survived. Protons and neutrons started to form within the first second. Within minutes, these protons and neutrons could fuse and form hydrogen and helium nuclei. After 300,000 years, nuclei could finally capture electrons to form atoms, filling the universe with clouds of hydrogen and helium gas. After around 380,000 years, it left behind a bath of photons, the cosmic microwave background that Penzias and Wilson accidentally detected. Within this were tiny ripples of matter that were stretched to enormous sizes during inflation, and in turn, these became the seeds for the galaxies and galactic clusters we see today. Today, when we look out at the universe, the full suite of observations we've collected, even with the known uncertainties taken into account, all point towards a remarkably consistent picture. Our universe is made of matter, obeys the same laws of physics everywhere and at all times. It's governed by general relativity, it's expanding and cooling and gravitating, and it's dominated by dark energy and dark matter, with normal matter, neutrinos, and radiation making up the rest. Today, it's full of galaxies, stars, planets, heavy elements, and intelligent and technologically advanced life in at least one location. These structures weren't always there, but instead arose as a result of cosmic evolution. In a remarkable scientific leap, 20th century scientists were able to reconstruct the timeline for how our universe went from a mostly uniform universe devoid of complex structure and consisting exclusively of hydrogen and helium, to the structure-rich universe we observe today. If we start from today, we can step backwards in time and ask where any individual structure or component of that structure came from. For each answer we get, we can then ask, okay, but where did that come from? And how did that arise? Going back until we're forced to answer, we don't know, at least not yet. Then, at last, we can contemplate what we have and ask, how did that arise? And is there a way that it could have arisen from nothing? To begin with, the life we have today comes from tiny particles that make up everything around us. These particles are like building blocks, and they join together to make complex molecules, which are the ingredients for life. These building blocks are made of even smaller parts called atoms. The atoms are like the basic elements that make up everything in the universe. But these atoms didn't just appear when the universe began. They needed a long process to form. This process involves stars being born, living their lives, and then dying. When stars die, they create new materials through powerful reactions. These materials are then used to make new stars, and the cycle continues. This cycle is necessary for things like planets and complex chemistry to exist. For the universe to have stars and galaxies like we see today, a few important things had to happen. Gravity had to pull smaller groups of stars and galaxies together to form larger ones. This required having some mass to start with, which gathered more mass due to gravity. To prevent matter from being lost into space during star formation, something called dark matter had to be present in the early stages. The right balance of different types of matter and radiation was needed to create things like the glow left over from the Big Bang and the basic elements. To make galaxies and other structures, there needed to be slight variations in the density of matter, and these variations grew over time because of gravity. The initial imbalances in density, along with the creation of dark matter and normal matter, were essential to make everything we see. So, when we think about whether the universe could come from nothing, these are the important things that we don't fully understand yet. Physics usually treats matter and antimatter equally, meaning reactions create or destroy both in the same amounts. At the universe's start, matter and antimatter could have been made in huge quantities due to its extreme heat and density. But somehow, the universe ended up having more matter than antimatter, even though they should have been equal. There are different ways this could have occurred, although we're not certain which happened. All these ways involve three main things: special conditions where things aren't balanced, which happens as the universe expands and cools; processes that break the usual rules and allow interactions that create more matter than antimatter. The standard model of physics allows for this through something called Sphaleron interactions, a way to create enough of a certain type of violation that helps make more matter than antimatter. The standard model includes these ideas, but they aren't enough by themselves. If you think of a universe with equal matter and antimatter as a universe with nothing, then it seems our universe did create something from nothing, even though we're not entirely sure how it happened. Likewise, there are various ways to create dark matter. We've determined through a lot of testing and research that dark matter can't be made of the particles found in the standard model of physics. Whatever dark matter is, it calls for new physics beyond what we currently know. Different possibilities exist for how it could have formed, such as being made during the early, hot phase of the universe and then not completely disappearing, so it remains stable. Forming during a phase change as the universe expanded and cooled, where big particles come out of nowhere, existing as a different type of neutrino, which could mix with regular neutrinos or be a heavier kind alongside the usual ones, coming about solely due to gravity, creating an extremely heavy particle. Why do we have dark matter today when the rest of the universe seemed to function fine without it in its early stages? There must have been a way to create this thing when it didn't exist before. However, all these possibilities need energy. So the question is, where did all that energy come from? Perhaps according to cosmic inflation, our leading theory of the universe's pre-Big Bang origins, it really did come from nothing. When we picture the very start of the hot Big Bang, we're thinking of something super hot, crowded, and full of energy. Now, when we wonder how this all came about, there are two ways to think about it. First, we can simply say that the universe was born this way. This means the initial conditions were set like this, and we don't have a further explanation. In the world of theoretical physics, we call this approach giving up. Alternatively, we can do what theoretical physicists love to do: come up with a theory to explain those initial conditions. We work to make predictions that are different from what the current accepted theory says, and then we go out to test those predictions. Enter cosmic inflation, which came from this second approach and changed how we see the birth of the universe. Instead of imagining the hot and dense start as an infinitely tiny, infinitely hot point, inflation proposes that before the hot Big Bang, there was a phase where space itself had an incredibly high energy density. This caused the universe to expand extremely quickly during inflation. When inflation ended, that energy turned into matter, antimatter, and radiation, creating what we recognize as the hot Big Bang aftermath. In more detail, this inflation not only makes a universe with the same temperature everywhere and a flat appearance, but also predicts specific kinds of variations in density. When we observed these variations, they matched what inflation predicted. From almost empty space, though it's space full of energy, a natural process has crafted the entire universe we can see today, full of structures. This is the big idea of how we could get a universe from seemingly nothing, although not everyone finds it completely satisfying. For many people, it's hard to imagine a universe without space, time, and the rules of physics. We can think of a place outside space, a moment beyond time, or conditions that aren't bound by physical reality. These thoughts make sense if we consider these aspects as things we'd need to remove to reach a true state of nothingness, at least from a philosophical standpoint. However, there's a difference between philosophical nothingness and a more scientific view of nothingness. There are 4 scientific ways to define nothing, each valid in its own context. A time when something didn't exist, an empty space. Space-time in its emptiest state with the lowest possible energy. Whatever remains when you remove the entire universe and its governing laws. If we use the first 2 definitions, we can say we've started with nothing and created a universe. But if we consider the third definition, it's not so clear. Unfortunately, we lack enough knowledge to say anything about the fourth definition. Without a scientific theory describing what exists beyond the universe and the laws that apply there, the idea of true nothingness lacks a clear physical definition. In the context of physics, it's impossible to make sense of an idea of absolute nothingness. What does it mean to be outside of space and time? And how can space and time sensibly, predictably emerge from a state of non-existence? How can space-time emerge at a particular location or time when there's no definition of location or time without it? Where do the rules governing quanta, the fields and particles both, arise from? This line of thought even assumes that space, time, and the laws of physics themselves weren't eternal, when in fact they may be. Any theorems or proofs to the contrary rely on assumptions whose validity is not soundly established under the conditions which we'd seek to apply them. If you accept a physical definition of nothing, then yes, the universe as we know it very much appears to have arisen from nothing. But if you leave physical constraints behind, then all certainty about our ultimate cosmic origins disappears. Many scientists suggest that the universe might have emerged from nothing, an idea rooted in quantum theory. This notion hinges on the concept that quantum fluctuations could trigger the spontaneous creation of a universe out of nothingness. However, this idea lacked solid support due to the absence of mathematical evidence. Enter Dongshan. He and his team from the Wuhan Institute of Physics and Mathematics. They've made a significant contribution by offering the first mathematical proof that the Big Bang could indeed be a result of quantum fluctuations. Central to this breakthrough are the Wheeler-DeWitt equation and the Heisenberg uncertainty principle. The Wheeler-DeWitt equation marks a significant step in the quest for a theory that encompasses everything. Back in the 1960s, John Wheeler and Bryce DeWitt created a mathematical framework that blends quantum mechanics and general relativity. This equation contributes to our understanding of quantum gravity, a key challenge in merging gravity and quantum mechanics. However, the equation's main flaw is that it doesn't involve time, so it's not a complete unification, but it's the best we have so far. On the other hand, Heisenberg's uncertainty principle is more widely recognized. In simple terms, this principle states that you can't precisely know both the position and momentum of a tiny particle. Otherwise, you'd break some important physics rules. From this principle, we realize that empty space isn't truly empty. In the vacuum, particles can briefly pop in and out of existence due to random quantum fluctuations. This concept also relates to the idea of the false vacuum. So, how does all of this come together to help us? Dongshan explained it like this. We showed that once a tiny true vacuum bubble is formed, it has the potential to rapidly expand. The WIPM team describes these true vacuum bubbles as perfectly round spheres. They use this knowledge to determine how quickly the sphere's radius can grow. They go on to analyze the bubble in 3 possible space-time geometries: open, closed, or flat. Interestingly, they found that the bubble's expansion would lead to a Big Bang. This new equation provides fascinating insights into the universe. The theory proposes that dark energy, the force driving the universe's expansion, could be linked to a concept called quantum potential. Quantum potential is a component of the pilot wave theory, a less-known interpretation of quantum mechanics that offers an alternative or complement to our current understanding of quantum theory. Pilot wave theory aligns with existing quantum predictions, resolves paradoxes like Schrödinger's cat, and introduces the idea of quantum potential. One of the drawbacks of pilot wave theory has been its inability to make distinct predictions. All its predictions are either identical to the widely accepted quantum theory or are not testable. That's where the new derivation from WIPM enters the picture. With quantum potential being a key element of this new equation, scientists might revisit the pilot wave theory. This fresh perspective could potentially advance our understanding of the universe by providing unique insights that go beyond what conventional quantum theory offers. Imagine a scenario where our universe wasn't born from a traditional Big Bang, but from a colossal collision between 2 gigantic, unseen objects in a higher dimensional realm. This is the essence of the ekpyrotic universe theory. In this theory, our universe isn't just the familiar 3 dimensions of space and 1 of time. Instead, it's a 4-dimensional brain that exists within a higher dimensional space. Think of this brain as a sort of cosmic sheet, floating in a larger reality that we can't directly perceive. The name ekpyrotic comes from ancient Greek, referring to a fiery, cataclysmic event. Just as a collision between 2 vehicles can create a massive release of energy, the collision of 2 brains in the higher dimensional space generates a burst of energy and matter that gives birth to our universe. This collision is like a spark that ignites the expansion and evolution of everything we see around us. This theory offers an intriguing alternative to the popular inflationary model of the universe's birth. The inflation theory suggests that the universe underwent a rapid expansion phase, driven by a mysterious field. But in the ekpyrotic scenario, it's not just the expansion, it's the result of a dynamic interaction between these higher dimensional brains. This concept doesn't just change how we think about the universe's beginning, it also introduces the idea of cyclical patterns. The ekpyrotic universe theory proposes that this collision isn't a one-time event. Instead, it suggests that our universe could be just one cycle in an ongoing series of collisions and expansions, with each cycle potentially leading to the birth of a new universe. Maybe the universe is a result of a colossal cosmic experiment conducted by an advanced civilization in a higher dimension. They created our universe as a simulation to study the emergence of life, matter, and fundamental forces. Maybe the universe is a mesmerizing projection that emanates from a higher dimensional realm, a concept that leads us to contemplate the profound idea that our reality is but a holographic reflection of an immensely intricate and multifaceted existence. Maybe the universe is a self-aware entity, a cosmic consciousness that came into being to experience existence in its myriad forms. This universe consciousness evolves through galaxies, stars, and living beings, accumulating knowledge and understanding along the way, like a universal self-discovery journey. Maybe space is like a phoenix in an eternal cycle of life and death. Maybe time repeats itself in an infinite recurrence of the universe after universe. Or perhaps this is the only universe after all, with a small hot beginning and a cold, dark finale, until the day comes when we discover how to extract more information from the universe than presently seems possible. We have no choice but to face our ignorance. The Big Bang still happened a very long time ago, but it wasn't the beginning we once supposed it to be. Imagine if we went back to when our solar system first formed and replayed that moment a billion times. It's very unlikely that humans would appear even once in those scenarios. But if we look back to the early stages of the hot Big Bang, a universe filled with stars, galaxies, planets like Earth, and countless opportunities for life to emerge becomes almost certain. This is because the rules and basic stuff of the universe stay the same. A universe born with certain materials will create specific elements. One with unevenness in density will make the first stars. The presence of dark matter will lead to stars with heavy components. When there's a second generation of stars, it results in planets like Earth and stars like our Sun. And when you have Earth-like planets, the possibility for life to thrive for a very long time appears. The rest might be influenced by randomness, but that's what allowed us to come into existence. It's now our responsibility to make the most of it. And that's it for the video. Thanks for watching, and make sure you also watch my video about cosmic inflation, and I'll see you there.